All right, so properties of limits. I'm going to still call this day one, part two. All right, so here we go. So basically up here we have all of your stuff that you've had all your life in mathematics. All right, so limits are still going to work, just like if you'd have a constant multiple going on. If you have adding or subtracting, you take the limit of each. And if you have dividing, multiplying, they all work just like you would with all of your other stuff. So let's look at example 1. So we have this information given. We have limit as x approaches c of your function f, whatever f is equal to 2. And then my limit as x approaches c of whatever g is equal to 3. All right, so even Nathan can do this first one. The limit as x approaches c of 5, g of x. Well, what's the limit as x approaches c of g of x? It'd be 3, so then it'd be 5 times 3, which is 15. That's how easy that is. All right, let's look at part B. So now we have a limit as x approaches c of f of x plus g of x. Well, what would this be? 5. This would be 5. All right, so we'd have the 2 plus the 3, which will give us 5. All right, let's look at this next part. Limit as x approaches c of f of x times g of x.
6.
That would be 6. That'd be 2 times 3, which we're going to call 6. All right, and then we have division going on this next part, so we end up with 2 over 3. All right, pretty good? All right. All right, I need another reader up in here, and Junior's going to be my reader for us. Go for it.
Finding limits by direct substitution. When tasked with evaluating a limit, the first thing you should always try is direct substitution. Direct substitution means that you...
Oh, I stole this. Go ahead.
Means that you substitute in the value that the variable approaches and determine what the expression evaluates to. As long as the expression does not evaluate to an undefined value, direct substitution will work.
All right. Did anybody else vomit when they read that? Okay. All right. So let's look at example 2. The first thing we should try to do is direct substitute. And if it doesn't work, we get like a 0 over 0. We have to look at it graphically or numerically, just like we did yesterday. So let's look at part A. Limit as x approaches 1 of the negative x squared plus 1. Well, what's x squared? If I substitute in 1, what is that? I get 1, but then I need to do what with it? Add a negative on it. So then I do what? What do I get?
0.
I get 0. All right. Now, that is very different, and I want to talk about the algebra of it. That is very different than that. Does that make sense? If I had a limit as x approaches 1 of that one, it would actually be what? That would be 2. However, order of operations matter. You do your exponent before you do your multiplication. All right, let's look at part B. So now I have a limit as x approaches 3 of this function. So I try to direct substitute. What do I get in my numerator? I get 2. What do I get in my denominator? Negative 1. So I end up with negative 2. All right, do I have a hole or anything going on these? No, they all work out, so we don't even have to do much. It actually is there. It would be actually clapping your hands, basically. All right, they'd touch. All right, let's look at this next part. Limit as h approaches 0 of 3h squared plus 2h. So I end up with 0. All right, let's look at this next part. The limit as h approaches 0 of 3x squared minus 2xh plus 5h. Well, what do I substitute in? 0 in for what? H. So what's left over? 3x squared. All right. And that's how we do that section. Let's start our homework practice. Today's going to be mostly a work day. All right.